Good evening my students, welcome to session 5, 15 CV33 fluid mechanics. So far the journey which we have travelled from the session 1 to 4 has covered most of the fluid characteristics starting from density, specific weight, surface tension. Today we would like to take problems on two. One is the capillary rise or drop and other one is the bulk modulus. Further we will travel in the fluid pressure and its measurements. So, welcome all. The outcome of the objective will be the student will learn the fundamental properties of fluids and its applications. Student will learn the hydrostatic law and application to practical problem solving. Today we are going to discuss two problems. One is on the capillary rise. I think you remember the video I showed to you. A small diameter tube will be rising high and a bigger diameter tube will be rising low, and at the same time I mentioned that there will be a capillary rise for water in which adhesion is more than cohesion, and there will be a capillary drop in case of mercury. Is it okay? So, this formula stands H is equal to 4 surface tension into cosine of the angle theta, which is angle of contact, divided by specific weight of the liquid into diameter of the glass tube. Is it okay? So, we are going to use this formula 4 sigma cos theta gamma L into D. At the same time we will take one problem on the bulk modulus K, which stands for change in pressure divided by volumetric strain. Delta P stands for change in pressure and the denominator stands for change in volume to original volume. Is it okay? So, based on these two we will solve the problem. Let us take the first problem. Let us read the statement. Determine the minimum size of glass tubing that can be used to measure the water level if the capillary rise in the tube is not to exceed 2.5 mm. Given the surface tension of water in contact with air is 0.0735 Newton per meter. Given the angle of contact theta as 10 degree 30 minutes. Is it okay? So, the question is very simple. He is asking you what is the diameter of the tube which is required to see that rise in the tube should not exceed 2.5 mm. Is it okay? Let us list out the quantities one by one. You can see the first one is given as surface tension sigma 0.0735, capillary rise is limited to 2.5 mm. No doubt my dear students, we are going to convert this 2.5 mm to meter by dividing it by 1000. Is it okay? Then comes contact angle theta 10 degree 30 minutes. Definitely 10 degree is no problem at all. 30 minutes we will convert here. On the right side I can see I have given a formula 30 minutes divided by 60 as 0.5. Is it okay? Assuming the specific weight of the water as 9.81 into 1000, which is 9810 Newton per meter cube. Is it okay? So, all the data are listed properly. The objective of the problem is to calculate the capillary rise H. We write the formula as 4 sigma cos theta gamma W into D. Substitute the values one by one. 2.5 mm converted to meter, 2.5 divided by 1000 is equal to 4 into 0.0735 cosine of the 10.5 degree divided by 9810 into D. This diameter if you calculate, it is coming around 11.8 centimeter. So, if you use a tube of 11.8 centimeter diameter, the capillary rise will be maximum 2.5 mm. Is it okay? So, this question was a straightforward question based on the formula which I am showing it by cursor. H is equal to 4 sigma cos theta gamma W into D. In this case H is given surface tension is given, angle of contact is given, specific weight is known, we need to know only diameter. Is it okay? Let us see the next problem. Next problem on the capillary rise is, let us read the statement. Water has a surface tension of 0.4 Newton per meter in a 3 meter diameter vertical tube, 3 mm diameter vertical tube. If the liquid rises 6 mm above the liquid outside the tube, calculate the contact angle. So, in this case, the given quantity is surface tension sigma, which is 0.4 Newton per meter. As I mentioned earlier also, surface tension is force per unit length. Is it okay? So, 0.4 Newton per meter. Diameter of the tube is given as 3 mm. We will divide it by 1000. So, we get 0.003 meters. The capillary rise is 6 mm, which is given, but contact angle is not given. Theta is not known. Assuming gamma W as 9810 Newton per meter cube, we use the formula of the capillary rise as, you can see the formula here, H is equal to 4 sigma cos theta gamma W into D. In this case, we are going to substitute H as 6 mm, which is 6 by 1000 is equal to 4, that is 4 into surface tension, the value is 0.4, cos theta, we do not know the value, we say theta, specific weight of the liquid 9810 water into the diameter of the tube, which is given as 3 mm converted to meter. You can see here 3 mm divided by 1000 is coming as 0.003. So, if you calculate this value, you get the value of theta. Is it okay? So, this is the way we have to solve the problem. The theta, if you calculate using your calculator, it is coming around 83.4 degree. So, this question also was a straightforward on capillary rise. Okay. In this case, you have been given the rise 6 mm, surface tension was known, specific weight was known, diameter of the tube was known, the only thing missing was angle of contact. So, we could work out what is the value of angle of contact, it is 83.4 degree. Is it okay? Let us take the next problem. This problem is slightly different. In this case, you can see here, determine the capillary effect in mm in a glass tube of 4 mm diameter when the immersed in first one water and next one is mercury. It means I am taking a tube, first I am immersing in water, then I am immersing in mercury. Okay. First I am taking this capillary tube of 4 mm, seeing here in water, what do you expect? You expect a rise, correct? But you take mercury, what do you expect? You expect a drop. So, this is a good question in which they have asked you both the things together. Determine the capillary effect in mm in a glass tube of 4 mm diameter when immersed first in water, second in mercury. Temperature of the liquid is 20 degrees centigrade and the values of surface tension for water and mercury is given as 0.0735 Newton per meter and for mercury and air 0.051 Newton per meter respectively. The angle of contact, that is when the water and air is there, angle of contact is 0 degree. Repeat, the theta value is given as 0 degree for water and air, while for the mercury the value is given as 130 degree. Given the specific weight of water and mercury at 20 degree centigrade as 9790 Newton per meter cube and gamma of mercury is given as 12,335 Newton per meter cube. My dear students, you know very well mercury is heavier than water. That is the reason the specific weight is 9790 for water and 12,335 Newton per meter cube. I have shown a small diagram, you can see on the right side. The same system with the same tube as I showed you earlier also by this one, same thing I am dipping with water, that is the first one. You can see the capillary rise will be positive, H more than 0, it will be rising here. And same tube we are dipping in the mercury, you can see there is a drop. Okay. So, we would like to know what is the value. Let us see one by one. First case we will take for water. Formula as you know very well, H is equal to, that is capillary rise or fall, is equal to 4 into sigma cos theta divided by gamma w into d, correct. Now, in this case substitute the value H is equal to 4 sigma 0.0735, which is the surface tension value, into cos 0 degree divided by 9790 into 0.004. What is the 0.004? You can see here diameter is 4 mm, 0.004 is there. Okay. Once you calculate this one, you get a capillary rise of 7.5 mm for water case. Okay. Let us take the second case. In this case, for mercury, the specific weight is 12,335, surface tension is 0.0735, diameter is 0.004, contact angle is 130. Substitute the value 4 into surface tension 0.051 into cos 130 divided by gamma of the mercury 12,335 into 0.004, which is the diameter. Okay. Repeat, 4 into 0.051 cos 130 and 12,335 into 0.004. You can see there is a dip of minus 2.66 mm. Is it okay? So, this question gives you an idea when the same diameter is immersed in water, it is rising up to 7.5 mm in water, but it is dipping 2.6 mm in mercury. Is it okay? Now, let us come to the last example of this part, that is the fluid characteristics, which is on excess of pressure. The surface tension of water in contact with air at 20 degree centigrade is 0.0725 Newton per meter. The pressure inside a droplet of water is to be 0.02 Newton per centimeter square. It means, see the unit here, it is Newton per centimeter square. When I have to convert to meter square, I have to multiply it by 10 to power 4. Is it okay? Now, you can see, calculate the diameter of the droplet of the water. We have to calculate the droplet of water. Given value is surface tension, which is 0.0725. Delta P is given as 0.02 Newton per centimeter square. I have converted here, you can see here 0.02 10 to the power 4 Newton per meter square. Let D be the diameter of the jet. Formula is excess pressure is equal to 4 times surface tension divided by diameter of the tube. So, we substitute the value 0.02 10 to the power 4 equal to 4 into surface tension value, which is 0.0725 divided by D. Repeat, delta P is given as 0.02 10 to the power 4. You can see here delta P is 0.02 Newton per centimeter square. I have converted to equivalent SI unit by multiplying by 10 to the power 4 is equal to 4 into 0.0725, which is surface tension of water in contact with air, divided by D. If you calculate this whole equation, you should get 1.45 mm or 0.00145 meter. Is it okay? So, this is a simple example of calculating the diameter for a given surface tension and excess pressure. The last example is on bulk modulus. Determine the bulk modulus of elasticity of a liquid if the pressure of the liquid is increased from 70 Newton per centimeter square to 130 Newton per centimeter square. The volume of the liquid decreases by 0.15. It means initially pressure was 70, I am increasing it to 130, correct. So, definitely the volume will, initially it was like this, it will reduce to small. So, it is reducing by only 0.15%. Let us apply to the formula. What is given? Initial pressure 70 Newton per centimeter square, final pressure 130 Newton per centimeter square, decrease in volume is 0.15 percentage. Let us see the formula. K value is change in pressure, which is 130 minus 70, which is a positive 60 Newton per centimeter square, divided by change in volume by volume. 0.15%, what exactly it means? 0.15 divided by 100. There is a decrease, this decrease and this minus sign will go together, you get 0.15 by 100 directly. If you calculate, you will get the K value for the bulk modulus elasticity of liquid as 4 into 10 to the power 4 Newton per centimeter square. So, this example gives an idea that though the liquid is incompressible, but to some extent it can be compressed. Maybe you can see at a high pressure 70 to 130 and it is going only by 0.15%. The bulk modular elasticity is 4 10 to the power 4 Newton per centimeter square. So, it is a very high value which is there. Okay. So far we have discussed the whole properties of the liquid, starting from the SI units, then we have talked about the specific weight, we have talked about the surface tension, we have talked about the fluid classification, we have talked about the Newton's law of viscosity, ideal fluid, liquid, all those things, bulk modulus, capillary rise, everything. I would like to ask you small simple question, you can make a note of it. The first question is like this: under what condition the meniscus between two liquids in a glass tube concave upwards and concave downwards? Repeat, under what conditions the meniscus between two liquids in a glass tube concave upwards and concave downwards? Is it okay? Answer that. What is the fluid? What is the fluid? I know you know, okay, you will answer. Fluid is which flows, right? What is the fluid and how they are classified? We can classify different way. So, please write. Next question is the third question. What is the difference between an ideal fluid and a real fluid? Okay, I will give a hint. Ideal fluid will be having viscosity 0, no resistance to flow, and real fluid will be having a real resistance. Okay. Next question is the fourth question. Why is it necessary in winter to use lighter oil for automobiles than in summer? To what property or to which property does the term lighter refers? Please look into that book or you can Google out also. It is a very good question. Why is it necessary in winter to use lighter oil for automobiles, maybe bike, maybe other vehicles, than in summer? To what property or to which property does the term lighter refers? Next is, what is the difference between dynamic viscosity and kinematic viscosity? So, one more question for you only. What is the difference between dynamic viscosity and kinematic viscosity? Right. The last one, the cite an example where surface tension play an important role. Cite an example where surface tension plays an important prominent role. Example I have earlier given, birds walk on water. Similarly, you find out and answer. Is it okay? I think I asked you a small 6 queries based on the discussion we have done in the 4th session and today some small session. Okay. Now, we march towards the next one. Let us come to the next part of the syllabi, fluid pressure and its measurement. This is again in the module 1. The learning outcome will be like this. You will learn to define the relationship between absolute pressure, gauge pressure and atmospheric pressure. You will learn to define the relationship between the change in elevation and change in pressure. Next one is describe the various types of pressure measurements instruments like manometers, mechanical and electronic type. So, we will be having this discussion, hopefully you are ready for this, correct. Let us see how the sequence will be. Our sequence will go like this. We will start with fundamental definition of pressure, pressure at a point, Pascal's law, variation of pressure with elevation, types of pressure, vapor pressure, measurement of pressure using manometers, introduction to mechanical and electronic gauges, then summary. So, we are going to start from the fundamental definition of pressure. Is it okay? But before I start, I would like to show you a very interesting thing. You can see a small animation I am showing you. Okay? You can see here also a bottle I am showing to you, exactly like a dam, like our KRS dam or Narmada dam or Bhakra dam, whatever you say. Definitely the water is this. This portion is the flat. So, definitely pressure is very heavy, it is trying to tilt more and more if you put exactly. So, we would like to know how is this pressure acting, though it is in static condition. We have seen dam, no, though it is in static condition, but it exerts a pressure. Definitely pressure is a force upon area, I know that, you know very well. The intensity of pressure small p is defined as P by A, capital P by A. A is the area, it is a two dimensional. Now, we would like to know more about it, how it varies and what are the properties which are important to be seen. Let us see what is the definition of pressure. We will start with a very simple concept. Pressure is defined as the amount of surface force exerted by a fluid on any boundary it is in contact with. Okay. Again I repeat, pressure is defined as the amount of surface force F exerted by a fluid on any boundary it is in contact with. It can be defined as force upon area. Let us take this one. You can see here there is a liquid here, water, and it is exerting pressure on the bottom. So, definitely this area is responsible. I will say this way, its area is important. This is the force exerted by this water column, correct. So, it is acting this way. Next one, the SI unit of pressure is the Pascal, which is 1 Pascal is 1 Newton per meter square. Also frequently used in bar 10 to power 5 Pascal. 1 bar is 10 to power 5. Anyway, we will come to that later, but one thing I have defined you, what is the pressure. Pressure is the force upon area. Now, you can see here pressure is a normal force. It acts perpendicular to surface. For example, if I take this only, maybe this portion, if I put a pressure, it will act like this. You can see the angle of contact between F and this particular plate will be 90 degree. Then you may be thinking, sir, if I tilt it like this, what will happen? Definitely you are right, it is going to be perpendicular like this. Suppose it is a curve like my hand, then it will be normal to the surface, correct. I repeat, normal, the intensity of pressure will be like this, it is normal. Inclined exactly like this, curved like this, is it okay? So, this shows you what is the pressure, and it always acts like a surface force or normal force, it is always normal force. Now, you can see in a pipe, if I suppose there is a pipe, maybe this pen is a pipe, in this assume that it is a pipe of water. So, pressure will be exactly which is shown in the diagram also, you can see it will be like this, it will be like a radial force like this, normal to the point of contact, point this point normal, point this point normal, this point normal. Let us see this one. This is a dam, again the pressure will be acting perpendicular to this inclined face. Here bottom it will be normal to this. So, mind it well, it is a perpendicular force or it is a normal force, and force is given by intensity of pressure small p is equal to F by A. This is the formula which is noted here. Is it okay? So, I have defined you exactly the next concept that is called pressure, which is F by A, and it is measured in terms of Pascal. 1 unit is 1 Newton per meter square. Is it okay? And it is always normal, as I showed you with example. Let us go further. Pressure at a point. Pressure at a point. I have not talked in a point. Now I am talking about pressure at a point. You can see here I have taken a point A, I have taken one more point A, one more point here, one more point here. Now, as an engineer, as a scientist, I would like to know what is the pressure here, what is the pressure here, what is the pressure here, and what is the pressure here. You may be thinking, is it same? No, it is not same. Then how it varies? What is the pressure here? Again it changes. So, we say pressure at any point in a fluid is the same in all direction point A. You take this point, in all direction it will be same, but at this point the magnitude will be different. It will be same here, but value will be more here, less here. We will see that later. Pressure acts perpendicular to surface. Definitely we are now more interested in the point pressure. Okay, now you understood. I am interested to know what is the pressure on the top, at this point, at the point A, at this point or this point. So, it will be varying place to place, magnitude to magnitude, but at that particular that molecule which is a very small element, we remember fluid continuum we talked. Yes, you are right, because fluid is continuous, all the molecules are continuous. So, if you take a molecule, that molecule you assume that this is a molecule, this chalk piece, okay, this is a molecule in a very big domain of C, everywhere the pressure acting is same. So, we will work out that. One more thing, the Pascal as I defined as the pressure unit, kilopascal is 1000 Pascal. Okay. So, now we will go for one small video just to show you a increase of pressure with increasing depth and its effect on structure. You may be thinking this structure is being affected by the increase in pressure and it is getting cracked, right. We say it is the toe, it is the heel, tension is more here, compression is more here, okay. Exactly like your shoes, when you push like this you put pressure here, positive pressure, but your heel, the back side, tension is there. Similarly, in the dam also same concept arises. I can illustrate here also, it is a dam, suppose it breaks. So, you can see this side pressure is more positive, but it is lifting this side, its tension is more. So, mind it well. Let us see one small video which shows the variation of pressure with respect to depth. Before I show this video, mind it well, it is a bottle in which maybe this bottle, I have put a hole here, I have put a hole here and I have put a hole here. Repeat, this is a bottle having a static liquid, liquid is not moving, one hole here, next here and the third is here. I would like to know how the pressure is varying. Let us see the magic. If you see here, you can see pressure is not at all there. Now you can see it is very high here, it is low here, high here, low here. Why it is more? Because depth is more. Why it is more? Because depth is more. Higher the depth, high will be the pressure. You can see the trajectory of the picture which you can see in this Grand Coulee dam also. You can see this one jetting out very fast in a arch dam. I can show the jet force. Can you see the force? That much force is coming in a jet when we are releasing water to canals or any downstream side. Pressure is very, very heavy. So, you can imagine we would like to know what is the pressure which is going to be there. I can repeat the same video just to show you. Higher the depth of the liquid, trajectory will be more, lower the depth of the liquid, trajectory is less. Is it okay? So, it totally depends upon the depth of the liquid and the specific weight of the liquid. Two things, intensity of pressure small p depends on two things. Number one, the specific weight of the liquid and the height of the liquid. Higher the specific weight, higher will be the intensity of pressure. You can see it is jetting out so fast, isn't it? And the effect you have seen already in this also. Is it okay? So, now we will go for next one, which is called Pascal's law. So far I have discussed you about the definition of pressure, about the intensity of pressure, pressure at a point. Now we would like to go for an important law which is called Pascal's law. This law says that pressure applied to a container or a contained fluid is transmitted uniformly. You can see here the term uniformly is very important to the entire fluid and to the walls of the container. You may be thinking, what is this going on? In the figure you can see I am putting a small force, maybe 10, and I am lifting 1000 here. How it is possible? This is what you see in the trucks and all, which is fitted with a trailer is there, not it is getting lifted. They apply very hand push and it is going to lift the whole trolley of that particular area and it is lifted. So, definitely this is very important. It says that pressure applied to a confined liquid increases the pressure throughout the fluid by the same amount. It means the intensity of pressure Px equal to Py equal to Pz at that particular point, at this point is same. It is called Pascal's law. This concept is being used in hydraulic jack. What they will do, you might have seen car jack, they apply very small force, right. Similarly, in the hydraulics also, what we will maintain this small P1 P2 is equal to F1 by A1 equal to F2 by A2. You say example, this is 10 by 1 and this is 1000 by 100. What is the ratio? It is 10. 10 by 1 is 10. 1000 by 100 is 10. It means one side you have F1 as 10, area as 1. In this case, force will be 1000 and area is 100. So, this concept is being used as an ideal mechanical advantage. This is very important. We use this concept to lift heavy machines by using the Pascal's law concept. Okay? You may be thinking what sir is telling. I will show you one small video. In this, I am having exactly like this glass tube, and I am having a small element there. The moment I press here, okay, here space is there is no space, it is going to apply equal pressure. You can see that element will come equally down. When I release the pressure, it will go back. Let us see the video on Pascal's law. Are you ready? Are you ready? Yes. Let us see. I am going to press this like this, I showed, no, exactly like this. So, you can see that element is moving down, correct. The moment I release, it is going back again up. It means the Pascal's law or the pressure, fluid pressure is transmitted equal in all direction. Repeat, the fluid pressure at a point is transmitted equal in all direction. It means at a point Px is equal to Py is equal to Pz. So, this is a very important concept. This concept is being used to lift big machines and all. The moment you release, you can see it is going back. So, this is a very fantastic video which is showing you how the Pascal's law is very important for our hydraulic applications. Is it okay? Okay, let us see next one. Now, we will talk about hydrostatic pressure. You may be thinking, what is this hydrostatic pressure? Hydra means water. Repeat, fluid static, fluid is a static, hydrostatic, water in a static condition. That is what it says. Let us see, read it, the first bullet. The hydrostatic pressure in a body of water varies with vertical distance measured from the free surface of the water. It means I have a free surface, I go down, pressure will be more like that. Then you may be thinking, okay sir, this diagram shows me a tank this side, a tank right side. There is a U-tube kind of a thing, inverted U-tube. If the liquid is same at 1 and at 2 and at 3 and at 4, repeat the mechanism. It is a tank on the left side, tank on the right side, and an inverted U-tube is there in which the same liquid is filled, correct. Is it okay? Now, the point 1 which is at a distance of say 5 centimeter, 2 same 5 centimeter, 3 5 centimeter, 4 5 centimeter. My dear friend, mind it well, as long as the liquid is same, the pressure at 1, at 2, at 3 and 4 all equal. Is it okay? Now, in this case you see, second case. Now, in the second case we have 2 tanks, but we have the same liquid also, but you can see there is a valve here. Can you see there? Valve closed. Repeat. In the second arrangement you can see the left side tank is there, right side tank is there, same liquid is filled, say water, but there is a valve here. This valve is there means though the 0.5 and 6 are at the same position, the pressure is not equal. Number third one, you can see here 9, 10, 7, 8. In this case oil is there, 7, 8 we have water. As long as it is water, 9 water, 7 water, and in 8 also water. So, in the left side 7 and 9 is water, right side up to 8 point it is water, above which oil is there. It means liquid is changing. So, as far as the pressure at 7 and 8 is concerned, it is same, because the same H2O. Pressure at 7 and 8 are same, but pressure at 9 and 10 is changing. Why? Because not liquid is not same, even head is also not same. So, mind it well, we are learning a very important concept. As long as the liquid is same, the level is same, it is same. But if there is an element like valve in the between, pressure is not same. The moment we change the liquid, again it is not same. Let us see the second bullet. All points on horizontal surface in the water have the same pressure. In this case 1, 2, 3, 4 we have equal pressure. Is it okay? So, we have learned a very important thing, that intensity of pressure will be same at the same depth for the same liquid. Is it okay? Let us see next one. Now, you may be thinking, okay, we have discussed so much, let us think one more important term, variation of pressure with elevation. Pressure in a fluid at rest, pressure in a fluid at rest is independent of the shape of the container. I am telling you purposefully, I will show a small example. Pressure in a fluid at rest is independent of the shape of the container. Number 2, pressure is the same at all points on a horizontal plane in a given fluid. Now, you can see this is a tank having a flat bottom, then triangular, then semicircular, again curved, then flat, trapezoidal, inclined, some erratic shape. As long as this liquid is same, water, at this point, and at this point, and all along this dotted line, pressure is same because the head is same. Okay? There is no effect of this inclined plate, of this circular shape, of this irregular shape. Let us see this also here. You can see here this particular container is having a typical shape, some zigzag shape is there. This is also having, assuming that this depth is same. So, the intensity of pressure at the bottom for the same depth, say 10 centimeter here and 10 centimeter here. You can see the previous bottle was plain, this bottle is zigzag, correct, but intensity of pressure at the bottom will be same for the same depth and for the same liquid. Is it okay? You can see again if you want, this is a plane more or less, and this is assuming that both depth of the water is same. So, the intensity of pressure at the bottom and at the side here, and at the bottom here, both are same. Is it okay? So, this is very important. This is called D'Alembert's paradox. We call it D'Alembert's paradox. Now, let us see how it varies with elevation. Now, we will be thinking, we are engineers, sir, we need to quantify. So, you can see I have derived a small derivation. We are taking a small element and the bottom and the top, the difference has been worked out with the force balance is equal to mass into acceleration, and you will not go to the details. This derivation directly tells intensity of pressure small p is having a triangular shape, y is equal to mx. You can see on the board also I have shown here, the h is the height, and at the intensity on the top pressure is 0, which is called gauge pressure now, and intensity at the bottom is gamma liquid into H liquid. Is it okay? It is a triangular variation, P is equal to gamma L into HL, right. Let us see next one. Now, one more thing, variation of pressure with elevation we have learnt, but we would like to use this. In a liquid with a free surface, pressure at any depth H measured from the free surface can be found by applying equation P1 minus P2 rho into G into H. Rho is the density of the liquid, G is the acceleration due to gravity, H is the force. It means at the water level, which is shown by a triangle here, the intensity of pressure will be 0. You are right, H small h is 0. You can see in the board also, when H is 0 here, intensity of pressure is 0 and the value is here highest. So, gamma L into HL. Same concept is being shown there. So, nothing wrong in that. We will go to the next one. Let us see a small thing before we go further. In this particular diagram, you can see here a pressure at B and A. Then you may be thinking, sir, the point A is the deeper, point B is at a higher elevation, but it is near to water surface. What is the intensity of pressure on the top? 0. Maximum here is. So, intensity of pressure at A will be more than intensity of pressure at B, correct? No? So, PA is more than B is true, correct? Now, at the point A for the same liquid, say mercury, at the point A for the same liquid, say mercury, the point C is also at the same depth in the tank. The statement says intensity of pressure Pa is more than Pc. You may dispute now because liquid is same. So, P is equal to gamma L same into H, Ha and Hc both are at the same position, say 10 centimeter and 10 centimeter. Definitely I have mentioned here Pa more than Pc, which is not correct. It is a false statement. It is a false statement. Which is correct? The intensity of pressure at A, that is Pa, must be equal to intensity of pressure at C, as long as the height is same, as long as the liquid is same. Is it okay? So, this has given you a small idea how it goes. Now, let us, so far we have discussed the pressure, force upon area, intensity of pressure, as I mentioned, always perpendicular to the surface, this we mentioned. We learnt that at the top, when the depth is not there, intensity of pressure is 0 and maximum here in the bottom, and it follows a triangular law, correct? Intensity of pressure is equal to gamma liquid into HL, right? After that, we have discussed the units of pressure, which is Pascal, 1 Newton per meter square, and 1 kPa is 1000 Pascal. I think you know 1 mega Pa 10 to power 6 Pascal. Now, let us see a very important definition called types of pressure. Now, I would like to measure pressure. Pressure, one method is I can measure from the bottom. The bottommost, we say it is called absolute pressure. You can see it is the absolute 0 reference which is there in the bottom. You can see the cursor. So, you can see any point I take, say 1, this is the absolute pressure at 1. Any other point I take 2, this is absolute pressure at 2. What does it mean? It means very clearly that absolute pressure will be always positive. I repeat, the absolute pressure will be always positive measured from the absolute 0, which is the bottom of the system. Then you may be thinking, why I am stressing more about the absolute pressure? Can there be any other method of measurement? Answer is yes. I am measuring the pressure from the 0 reference. So, it will be always positive, like our temperature Kelvins, 0 degree, correct? It is not centigrade. Centigrade can be minus 25 also, correct? So, absolute 0 pressure always positive for 1 and 2 or 10, correct? Now, I am going to define one more term called gauge pressure. Why this is more popular compared to absolute? Question is that. Why gauge pressure is popular? At any place, say in Bangalore, say in Delhi, say in Trivandrum, or say any place, there will be a local pressure because it is at a height at mean sea level. If you take our Mangalore, it is at 0 mean sea level. Our Bangalore, it is around 600 above meters above mean sea level. So, we say a standard local pressure called gauge pressure. I repeat, it is a standard local pressure called gauge pressure. What is this gauge pressure? This gauge pressure is 760 mm of mercury. This gauge pressure is, you can say 1.3 kilopascal. It could be 10.3 meters of water column. This is the gauge pressure. So, if I measure the pressure above the standard atmospheric pressure, it is called positive gauge pressure. If I measure upwards, suppose if I measured downwards, it means you understood that the absolute 0 is 0 and gauge pressure is this distance. This value is 10.3 meters of water column. Okay. Now, suppose if my point is here, it is above the gauge pressure, it is a positive gauge pressure. So, for the point number 1 which is shown here, we get positive gauge pressure at 1, correct. But you see there is one more point called number 2, which is below the atmospheric pressure, which is below the atmospheric pressure, a tunnel. In that case, it is called vacuum pressure. It is called vacuum pressure, but mind it well, gauge pressure can be positive or negative based on the its level above the atmospheric pressure or below the atmospheric pressure. If it is above, like in 1, we say gauge pressure at 1 is positive. But you see number 2 is absolute pressure is positive, no doubt, but there is a vacuum pressure, it is called suction pressure, which is called negative pressure. Is it okay? So, mind it well, my dear friends, we are going to refer about both absolute pressure as well as gauge pressure. Okay? Let us see the next one. We have one more important pressure called vapor pressure. You might have heard this in physics also. When the pressure of a liquid falls below the vapor pressure, it evaporates. It changes from liquid state to gas. I will come back to this bottle again. You can see there is a liquid here, correct, and pressure is there. Suppose if I go on reducing the pressure inside this container, slowly it will go to the very low value and it goes very near to the vapor pressure at that temperature. What will happen? These liquid molecules which we are seeing as a, you can see, no, it is going to evaporate there. It is going to evaporate, and that vapor is going to exert a pressure on the liquid, which is shown in the diagram also. You can see with a red and bubbles are there. We are seeing here it is coming as these bubbles are there and it is being formed and it is exert a pressure. So, there will be a balance between the liquid which is going from the system and coming. The moment it balances, it is called saturated vapor pressure. We say SVP at that temperature, saturated vapor pressure. It means 1000 molecules are leaving and 1000 molecules are coming. That pressure is called vapor pressure. Definitely, this is a very important phenomenon in the hydraulic turbines, in machines and in many more industrial applications, in which the pressure is very important, where it is going to start boiling and all. That actually phenomenon is called cavitation. We will come to that later, not now. So, one thing is very clear, pressure exerted by the vapor is called vapor pressure, right, it a given temperature and pressure. So, the intensity is measured as Newton per meter square, which is very important. The importance of vapor pressure, in case of hydraulic turbines, sometimes pressure goes below the vapor pressure of the liquid. The liquid which is flowing, sometimes because of the change in geometry, because of the change in the energy, that pressure is going below the vapor pressure, those bubbles are formed. These bubbles are formed and they are carried to a high pressure region, they collapse. You assume that this is a bubble and it is formed in the cavitation area and it is now travelling, and this is the wall of the, you can say, turbine, and it is going to collapse there, it is going to bombard there. That collapsing of bubbles, which is called a cavitation bubble, will induce excess pressure, number 1, will induce high vibrations and will induce noise also. Suppose you have in your home one valve is there, water is flowing, try to stop, you will listen some sound in that. That sound is nothing but the hammering action, that we will come to the next module. But mind it well, these cavitation bubbles which are formed because of the vapor pressure are going to bombard the walls of the turbine, walls of the pumps and walls of the machines, and they are going to cavitate, eat the material like a blisters in the system. They will induce vibration, they will induce noise, that is cavitation bubbles. You can see in some of the vehicles, you might have heard in the bikes and all, suppose you increase, there will be a knocking sound, but something like that. Exactly, it is because of the cavitation and the knocking sound, because you are not able to control the vapor pressure or petrol and the air, because of that it will happen. So, in carburetors, in the sprayers of liquid, these are very important. Vapor pressure of the liquid is very important, it should not fall below a certain limit, otherwise bubbles are formed. These bubbles, they collapse, they eat the material, they induce vibration, and all these problems are there. So, vapor pressure is a very important consideration. Now, let us start a small part of it, measurement of pressure using manometers. I will stop with this slide only. So far we have discussed about the definition of pressure, intensity of pressure, how it varies in the liquid, P is equal to gamma W into H. Now, we have to develop some instruments which can measure. We have talked about gauge pressure, we have talked about absolute pressure, and we have talked about cavitation bubble through Weber pressure, correct. So, now we want to measure the pressure. The pressure can be measured in an industrial platform, pressure can be measured in a dam, pressure can be measured in turbines, pressure can be measured in pumps and any hydraulic application, okay, even in tire also. Now, we would like to know which are the instruments which we are going to use to measure the pressure. They are divided into 3 categories. You can see the cursor. One is the manometers. You can see here also I have shown a diagram here. It is a manometer. Okay. One category is manometer. It is basically a tube, glass tube balancing the liquid columns, which is called manometer. We will talk to this later also, but first one is manometer. Come back to the slide. Next one is mechanical gauges. Mechanical gauges you might have seen in factories, mechanical gauges you have seen in the petrol pumps, right, and mechanical gauges are there always in many industries. So, they are very useful. Even in small hotels also I have seen where they make this idli chamber and all, no, idli making, there also they put pressure gauges and all. So, mechanical gauges. And number 3 are most ultra modern, they are called electronic pressure measuring devices. So, with this I will stop here and hope tomorrow you will join me to understand what are the types of pressure measurements, how they work, what are the numericals we are going to see, and how accurate they are going to measure the pressure, which is our current topic of discussion. Thank you very much.